more problem. Problem 3. It's a shorter problem. It's just a fracture mechanics introduction kind of little sampler kind of thing where we have here we got a pipe that's got a crack in it, a radial crack, 7 millimeters deep. The pipe is a 6-inch Schedule 160 pipe, which is a Schedule 160 is a very, very, very thick-walled pipe. The dimensions, actual dimensions, are 168.3 millimeters outside diameter with a wall thickness of 18.24 millimeters. And it's made out of AISI 4340 steel, quenched and tempered at 650 degrees, and it carries 100 megapascals internal pressure. You don't actually need that, but that's okay. I just accidentally put it in there. We want to determine the maximum safe pressure if a safety factor 1.5 against fracture of the correct pipe is desired, right? So what I'm going to do is I'm going to find that safety factor, and then I'm just going to use that along with my 100 megapascals, I think, to work backwards and get what it was. I think that's what I'll do. I don't know. I haven't decided yet. So anyway, I wrote out the problem, kind of summarize the idea. Let's see. So some of the things I need to get are looking in the book. If I can find the book. What do I do with the book? There it is on the floor. There. Okay, find the book. First, let me look at the material stuff. All right. So I gave you sort of I think I told you in class what you might need to do for this. But let's see, here's the heat-treated ones over here in this table, A21. And we could see that we have 4340 quenched and tempered at 650, right? Now, the thing that's going to be useful to us is we're going to see that it has a yield strength of 855. I'm going to keep my thumb or my finger in here as we go over to the section of fracture mechanics and take a look at the materials. You'll see that we have two of these 4340s, right? We have this guy and that guy, and they give us the fracture toughness or critical stress intensity factor, either way you want to think of it. But there's two different ones. Well, you can see that the yield strength is 860. Yield strength here, 855. This must be the one, right? So that's the thing that you were trying to do here. So we're going to go with this guy of 99 megapascal square root meters. That was the idea. I know. It's just... All right, so our critical stress intensity factor from table 5.1. Right, the entire thing, the entire chapter, that's like the end of the chapter, and it was the first table. There weren't many tables known. 99 megapascal square root meters. Okay. Other things we were going to want to do. Well, let's take a look at the applicable fracture mechanics thing, right? Oh, look, there it is right there. And looking at it here, we see cylinders subjected to internal pressure having a radial crack. Use equation 350 for tangential stress, where the R is equal to RO. So they kind of give us the instructions of what to do, right? So let's look at, but before we go there, let's pull off what we need to off of this while we're here. We need an RI over RO. We need to look that up, and we need an A divided by RO minus RI, right? So let's take care of those things. So I probably want to get the RI and the RO. So RI should be equal to, well, let's go RO. Let's go RO first. RO is just going to be 168.3 divided by 2. And Mr. Calculator, you'll be needed because I can't do that in my head. Should be able to, right? 84.15. Yes, seems like I should be able to do that. Millimeters. And then, so RI is just a RO minus the thickness, right? And didn't leave myself enough room, dummy. 84.15 minus our 18.24. So we end up with 18.24 minus, so you get 65.91 millimeters. And what did we need? We need Ri over, is that right? Ri over Ro. So 65.91 divided by 84.15. 84.15 divided 0.7832. Not too far off for 0.75. 0.75 is one of our lines. That's good to know. And then we have an A divided by RO minus RI, which should just be the thickness, right? Yeah, that should just be the thickness. Why don't we just do that? I don't know. So that's going to be 7, and I guess I'll stick with this even though it's kind of ridiculous. 84.15 minus 65.91. That should just be 7 divided by 18.24. And that's all I'm going to do, because I'm too lazy. 18.24 divided. So I get 0.3838. See if we can get a pretty decent. So we got 0.783 and 0.3838. All right, so let's see. Zoom in. All right. And here's 0.75, but we're at 0.78, so maybe just slightly above it. And here we're at 0.3838. Here's 0.3, so here's like maybe 0.38. It's like right in there. I'm gonna say that we're like kind of like right in there, maybe. So there's 1.4. Here's 1.6. 1.5 is right here. That's not true. 1.7 is right there. So I'm gonna say it's 1.65. 1.65. I've decided is close enough for our beta. Approximately 1.65. From figure 530. All right, so now we need, okay, so we were told to use from this guy right here. Let's pull him back up. We were told to use equation 350 with, and by implication here, we're only going to use hoop. We don't use longitudinal, do any other stuff. So we're just going to use hoop stress, which I think is 350. And R is going to be set to the outside radius right there. Right. So I think I might have, in a previous problem and at some other time when doing doing this same thing, used the stress at the bottom of the crack, which makes more sense to me. But they gave us instructions, so we're just going to do. This is what this thing is based on, so we should follow along. All right, so there you go. There is the hoop stress, and we'll write down that equation. That's the one we have here. So the stress to use is simply going to be Ri squared times P divided by Ro squared minus Ri squared, and then 1 plus Ro squared over R squared. Right. Now you know when you stick Ro in there, this just turns into 2. So that makes it a little bit easier. Now I'm going to go ahead and find the stress. Even though I don't actually need to, I could work backwards and find what P is going to be. I don't know. We were given the 100 megapascals, but we didn't actually need it. So kind of going back and forth whether I would want to whether I'd even want to use it. It kind of makes more sense not to use it. I don't know. Ri is 65.91. Square them. The pressure, we'll go ahead and stick them with 100 megapascals. I think I was just going in autopilot or something when I was writing that. 65.91 squared. And we could just make a 2 here, because we know that's going to be 2. And so 65.91 squared and 84.15 squared, but we're subtracting out 65.91 squared, and then we're dividing them. That comes 1.587 and multiplying it by 2. So what we could just say is it's 3.174 times P, but we'll go ahead and multiply it by 100. And so we get 317.4 megapascals of stress, hoop stress. And we know that the equation that we use for this is Ki is equal to beta sigma square root pi A. So we're going to take a 1.65 times our 317.4 square root pi, and now we need to use because it's megapascal. This is in we want this in megapascal square root meters. This crack needs to be in meters, so 0.007, right? And I'll go down to there. We're going to say 0.007 times pi, for some reason, I don't know, square root, and then multiply, and then 1.65 multiply, and we end up with a 77.67 megapascal square root meters. This is our stress intensity at that. So we could find the safety factor from fracture is going to be KIC over KI. And so we're going to take a 99 problems, right? 77.67, and we end up with 1.27. I'm going to use this for a calculation, so I more than 2 decimal places this time. So our P max, right? The idea there is we could say, well, they're proportional to each other, right? There was nothing. This was, they're all in there. So we say that we're going to take 1.275 times my 100, and I'm going to end up with 127.5 megapascals is our maximum. So that's going to be our answer. And I didn't necessarily have to do it that way. I mean, I could have just left this pressure right here as a value and then solved for it right here after setting this equal to 99, and I would have gotten the identical thing. By the way, this is the last digit right here was a 4.6, so when I rounded down I still had 127. So you can put 128, I don't care. But that's problem 3. And it's just a taste sampler test thing, just to kind of get you, hey, fracture mechanics is a thing, right? And it's a different way something will fail, material will fail if it has a crack already into it. Different than stress, and it's different than stress concentration. Ta-da, done.